If we take a look at practice question set number 5, starting with question number 1, we see the info box that says at a coal mine, a train engine bumps an empty hopper car that has a mass of 10,000 kilograms, such that it rolls at a constant speed of 2 meters per second under a coal storage bin. The hopper car triggers an electromagnetic switch on the track below the storage bin. The bin drops a load of 12,000 kilograms of coal onto the hopper car. And then we want to find, ultimately, we want to find how fast is the hopper car and the coal that's now in the hopper car moving immediately after the hopper car receives the coal. Now, if you're not careful here, you can get a little bit confused by the wording of this. We see a train bumping a hopper car. That looks like a collision, right? And in fact, it is. But it's a collision that doesn't really matter to us because we're told that as a result of that collision of the train with the hopper car moves with 2 meters per second. What we really care about is the collision of the hopper car that is moving at 2 meters per second as a result of the train moving or hitting it. The collision of that with the coal that's moving downward. Right? Does it make sense? Now, let's take a step back from the context of this question. Let's just look at the diagram that I'm drawing right here. We've got one object moving to the right, one object moving down. Independent of the context of this question, where do you think, where would you predict the coal/hopper car to go? Where would you expect the two things that are now combined to go, Benton? Down and to the right. Yeah, exactly. Okay, that's exactly where you should predict it to go. Theoretically, this should go down and to the right. But realistically, in practice, we know that doesn't happen, right? In practice, when this coal falls into this hopper car, what happens to the hopper car? Well, it slows down because we've now got more mass, right? It slows down probably by a factor of about 2 because the mass is just doubled, almost doubled. Speed's going to be about half of what it was. Realistically, practically, we know that it's going to move horizontally, though. It's not going to go down and to the right because the track is in the way. The earth is in the way, right? Well, let's treat this question right now as if we don't know that it's going just horizontal afterwards. Okay, let's treat this question as if it could move down and to the right, okay? And you're going to see how we resolve this little conflict, this apparent conflict between theory going down and to the right and practice where it just moves to the right. Okay, let's look at our x and y components here. We're going to say pi is equal to pf, as we always do. m1 v1i plus two objects here, two terms, m2 v2i equals, now the coal becomes part of the hopper car, so the mass of this will be combined, we'll just call it mt times vf. Is that good? All right, let's step in some numbers here. M1 is the mass of the hopper car, that's 1 times 10 to the 4 kilograms, times v1i, which is 2.00 meters per second. M2 is 1.2 times 10 to the 4. What's v2i? As I look at the x-axis here, 0, because it's moving downward. Right? We don't even know how fast it's moving downward, but we know it's moving just downward. So we're going to say plus 0 equals the total mass, 2.2 times 10 to the 4 times VF. We solve for VF here, and when we do, we get 0.909 meters per second. That's the velocity in the x direction. Now, realistically, we know that it moves only in the x direction, right? So that's my answer. We'll figure out how to express that in just a moment, but why? How do we know to stop there, though? Yeah? But like in theory, it should go down and to the right. There's the ground there, but why doesn't it go down to the right? Okay, normal force going up. Okay. We're going to go a little bit deeper into that, though. When I examine only the horizontal, we have a hopper car with a certain amount of momentum, and then the coal goes in the hopper car and keeps moving horizontal. The only two objects involved in this horizontal collision are the hopper car and the coal. Coal adds more mass to it, so it should slow down, but otherwise it keeps going horizontally, right? But what about vertical? Vertically, the coal hits the hopper car, and the hopper car starts going, hopper car / coal combination starts going down. If the hopper car and coal starts going down, what must go down with it? What object must go down with the hopper car and the coal?
The train track.
The train tracks, which are attached to the
Ground.
earth. Listen, the earth becomes part of the system vertically, right? You push down the train, well, then you got to push the earth down with it. So if you're going to analyze the y component, you go ahead, try to analyze the y component. The final mass becomes like 10 to the 24 kilograms. What's that going to make the final velocity y component? We've increased the mass from 10 to the 4 to 10 to the 24 because the earth is now involved. The velocity goes 0.000000. I don't know how many zeros it would be, but a lot. Basically, the final velocity y component becomes what? Nothing. Becomes 0, right? That's why we don't have to do the y component. There is a y component here, but it's so small because we've increased the mass by so much because the earth would need to be included that it just doesn't matter. When you look at that Physics 30 and 13 page document that I gave you, topic 16K on page 3 says problems involving the earth. That's what I mean by that, problems involving the earth. When the earth becomes part of the problem, we increase the mass so much that we don't need to look at the y component. Like even though it's there, it becomes so small that it's effectively irrelevant. So in practice, this doesn't go down into the right a measurable amount. It does go down into the right, but it goes down into the right with the earth. So it's such a minuscule amount that it would never be able to be measured. Does that make sense? So what's our answer? Well, this combined with this, however many zeros it should end up being, when I combine this with this, it becomes just this, right? So my answer is 0.909. I'm going to express that in scientific notation because that's the way they asked me to do that. 9.09 times 10 to the negative 1. Now we want to record the value of B. So what's B? 9?
9.0.
Yeah, B stands for the base. In the base, they tell me to record to 3 digits. So my 3-digit base is 9.09. Not 9, not 9.0, but 9.09. Got it? Okay, don't quote me on this, but this is going to arise somewhere for sure. I believe it's on your unit test. I think it's on your unit test. Another question where the Earth becomes part of the system. And when that happens, you're not going to look at that y collision, that y-axis collision. You're only going to look at the x-axis, even though technically it's a two-dimensional thing. Okay? So be prepared for that sometime in the next week, because it arises somewhere. I can't remember if it's your unit assignment or a quiz or a test, but I think it's your unit test that's coming up on Tuesday. Okay, let's take a look at the second question now. This one I like too. Sheet of curling ice, red curling rock hits a blue curling rock. Glances off. We call this a glancing collision, where one thing bounces off another and goes at a funny angle, a glancing collision, versus the T-bone where they're at 90 degrees to each other. I like this one because A, they give me the diagram already. I don't need to draw it. B, what else do I like about this?
Sports.
Yeah, okay, it's sports.
Two funny angles.
Yeah, you do have two funny angles, which I don't like, but the masses are the same, which means that ultimately we know we're going to cancel them out. And X and for what, right? You said we have two funny angles. We do, but watch this. Be careful of this. This funny angle we don't know what v is, right? We're trying to find the value of v here. Usually we don't have that value, right? Usually we get the 1, and then we're trying to find v and theta, right? So we're given more information here than we usually are. Usually we're given one funny angle, and like we look at this and say, like, oh, 2 funny angles, that makes life hard. No, it shouldn't make life harder, should it? If we're given more than we're usually given, shouldn't that, at worst, at best, make it easier, make it better for us, or at worst, make it the same? There is a shortcut that occurs as a result of being given this angle of 23 degrees. By the way, I call that, when we're given an angle that we're not usually given, I say that we're given the unknown angle, because that's usually the unknown angle. But this time we're actually given that value. There is a shortcut, and I'll tell you about that shortcut, but only after we do it the regular way, the non-shortcut way. Okay? Let's pretend initially that we don't have that 23 degrees. That's what you should do, right? If you don't know how to deal with something that you're given extra, just pretend you don't have the extra. Like, seriously, think about that. If you could solve the question without being given that angle, don't let that angle confuse you. Solve it without that angle. And if you do spot the shortcut, then that's fine to take advantage of that. But don't lose any sleep if you don't notice the shortcut. Okay, diagram's drawn for me. What do I do next? I'm pretending, remember, that I don't have that angle. I'll show you what to do with it as far as the shortcut goes later. What comes next? You so know this. Get rid of the funny angle. Let's take the 0.14 over here. 67 degrees. This is x, this is y. The x component can be found by the cosine function. When we do that, it comes out to be 0.0547 meters per second. And the y component is found by the sine function. It gives me 0.12887 meters per second. And then we're going to box that off, because that's what we do. I do that every time. Like, does that, like, if you didn't put a little box around it, would that be the end of the world? Probably not, right? But there is value in structure. Really is value in structure. If we do the same thing every time, then it becomes kind of old hat, right? And it becomes easier to do when it becomes routine for us, right? When we do the same thing every time. Okay, we got this. Now let's do our x's and y's here. Pi is equal to Pf. We're going to say m1 v1I plus m2. What should I write in next? 0. Blue rock is at rest, right? Equals m1 v1F plus m2 v2F. Nicole, what did you say I could do? Simplify this a little bit? Yeah, because it's the same mass in every term, I can cancel that out, right? v1I in the x direction is 0.36. v1F is what we're looking for here. And v2F is, remember, it's not 0.14, because that's gone. We're never going to use that again. What do I use for v2F here? The blue rock. What is it? Yeah, good. 0.0547. I'm just going to highlight that to remind us where it came from. Then we solve for v1F. Take that to the other side by subtracting. v1F works out to be, for the x component, 0.3053 meters per second. Oh, even better for the y-axis here. What's the initial y momentum of the red rock? Somebody said it? Yeah, you're right, 0. What's the initial y momentum for the second rock, the blue one? 0, because it's at rest. So we're going to say the initial momentum is 0 equals m1 v1F plus m2 v2F. Nicole, did the masses still cancel here? Looks a little bit different than it did up there, but still in every term. Well, it's a 0 over here, but that counts. V1F plus V2F. Remember, it's not 0.14. What is it? Parker, what's the y component of the velocity here? Yep. 0.12887. Good. Both positive because they're both up here. Highlight that just to remind us where it came from. And then now it's easy, right? Now it's grade 10 math. We combine them. Whoops. Let's try this. There we go. 0.3053. And, oh, what was V1F? Negative 0.12? 0.3053 to the right, 0.12887 down this way. What do we end up getting there? 0.33. Answer C. Good. What do we not use here? What do we not use because we didn't need to? Yeah, the funny angle that we were given, that we're not usually given, right? We call it the unknown. We were given the unknown angle. It's not really unknown because we're given it, but that's what we say. We're given the unknown angle. We didn't use it. What do you think you'd get if you use the inverse tan function to solve for that angle? You better get 23 degrees. If you don't, you know you've made a mistake, right? That's a nice little check, actually. Okay, if you did it this way, and then you turn around and calculate theta, and you get the same angle as they gave you, like you must have done everything right. Now, does anybody spot the shortcut here? Anybody see something that I could do to save some work here? Yeah, awesome. Yeah, I do need to just find one of the components. Like, let me erase this, all of this. The y component and all of this. Austin, if I have that one component, what do I do with it? Yep. I know the x component is 0.3053. What's the y component? Don't know. What's the hypotenuse? I don't know. That's what I'm trying to find. But I do know the angle is 23 degrees. So if I have theta and I have the adjacent, couldn't I just say cosine 23 degrees is equal to adjacent over the hypotenuse? What did we say it was? 0.33? Yeah. This is quicker, but it's no more correct. Do it the way that's easiest for you. Take advantage of a shortcut if you see it, but don't spend 5 minutes looking for a shortcut that's going to save you 1 minute. That's not a very good use of your time. If you see a shortcut, do it. If you don't see it right away, don't worry about it. Just do it the regular way. Do it the longer way. I will tell you that in the last little while, the last number of exams, when they give us one of these questions, they tend to, not always, but they tend to put a shortcut or two in there. Reason being is, like, these are long questions, right? For a 1-point multiple choice or numeric response, they're long questions. So they often give us shortcuts, like being able to cancel the masses or being able to do this. But you understand, you don't ever have to take advantage of those shortcuts. If you spot them, good. If you don't, oh well. Right, one more question here. Next question is multiple choice number 2. So the hole is drilled in a boulder that has a mass of 250 kilograms. Explosive charge placed in the hole. The boulder exposed into 3 pieces. 90 degrees are right angles to each other. what's the magnitude of the momentum of the 90 kilogram piece? Our problem with this one is that we're not told which way these pieces go, right? We go at right angles to each other. So there's a bunch of different ways that we could draw this. We got the way that I drew it. I said object number 1 goes off this way, has a mass of 110 kilograms and a velocity of 4 meters per second. I said object number 2 goes off this way, has a mass of 50 kilograms and a velocity of 10 meters per second. And therefore, object 3, fragment 3, goes off this way. Now, in the end, it doesn't really matter how you draw it as long as those first 2 directions are perpendicular to each other. Your object 1 might become object 2. Your x component might become my y component. But in the end, we're going to get the same answer here. We're told they're perpendicular to each other. It doesn't define how they're perpendicular to each other. Okay, let's do our thing here. Let's say for the x component, 0, because that's the initial momentum, is equal to m1, which is 110 times 4, plus 0, because in mine, object number 2 is moving on the y-axis, plus m3, which is 90 times v3f. v3f works out to be negative 4.8889 meters per second. How many people got an x component of 4.8889 or negative? How many people got a y component of 4.8889? Yeah, so if you got a y component of that, that just means that your object number 1 was up or down and object number 2 was left or right. Okay, that's not wrong. Okay, that's just the way you decided to draw the picture versus the way I decided to draw the picture. Okay, y components, 0 initial momentum again is equal to 0 for the first one plus 5.0 times negative 10, because it's 10 down, plus 90 times v3f. And v3f works out to be, for mine, works out to be 5.5556. All of you should have gotten 4.8 and 5.5. You might have got negative where I got positive, and you might have got x where I got y. But you should have got both of those numbers. We combine them. 4.8889, 5.5556. We don't need to find the direction. We're just looking for the magnitude here. When we do, we end up getting 7.40037. So the answer would be A. Correct? 7.40. Nick's kind of like, I think I see his head kind of doing this. Hey, Nick, what's wrong? Yeah, this is the perfect example of a question that illustrates the RTQ, ATQ thing that I have on the backboard there. Read the question, answer the question. Read the question. What are we looking for? Momentum. What have we just found? Velocity. You want to find momentum, say P is equal to m times v, and you multiply those together. You're going to see in a second why this question gives us so much trouble. That's why it gives us so much trouble, because it's a devil question. 666. Did anybody actually tell me, did anybody calculate, instead of calculating V3F here, up here, anybody calculate P3F? The momentum of the third piece? You calculate PF here, PF down here, and then resolve the momentum vectors, and you would get 666 right away there without having to multiply it by mass, because you would have already taken care of that. Either way is fine. They're both correct. Okay, Janae, you set yours up differently, but you still got 666, right? Because you made them 90 degrees to each other. And that's all we needed to do in this question.